In the last class, we have seen that in quantum level, the commutators between the charge q and the field phi, okay, such that epsilon alpha q alpha with respect to the phi a will generate an infinitesimal transformation given by minus I epsilon alpha fa alpha. So in today's class we will see how to understand the conserved charges at quantum level. Okay. So in quantum level, the charge q and the current density j mu alpha will become quantum operator. It becomes quantum operators. Okay, since q is conserved, it is time independent operator. Okay, since q alpha is a conserved quantity, okay, q is conserved because it is corresponding to some symmetry, right? Therefore q will be time independent operator. This charge can play a more important role. So we will very soon see that the charge q can be viewed as a generator of symmetries. Okay, so we will show that the commutator is minus I epsilon alpha fa alpha, where this is the infinitesimal transformation. Which means that this commutator of q alpha and epsilon alpha with phi a generates an infinitesimal transformation. Okay, therefore q, the charge q can be viewed as a generator of symmetries. And this infinitesimal transformation we have already discussed in the previous classes, that phi a prime is equal to phi a plus epsilon alpha fa alpha, which is a function of the field and the derivative of the fields. Okay, so therefore q alpha is also called as generator of symmetries. Now suppose in this transformation, okay, fa alpha does not contain the time derivative of the field. Okay, so we are just going to see the first case, case 1, where fa alpha does not contain, that is this function does not contain the time derivative. That is this term. Okay, and also the k0 alpha is equal to 0. Okay, so this is a limited case. For example, if you look at the translation symmetry, okay, which give rise to the stress tensor. So the stress tensor T mu I. Okay, so this is the conserved current corresponding to the spatial translations, right? So the I is the alpha here actually. These are corresponding to different symmetries. So this applies to all internal symmetries. By internal symmetry, we mean that the transformation that don't involve the space and time coordinate. For example, a rotation, the phase rotation of a complex scalar field, that is known as an internal symmetry. Okay. So when we do spatial translation, then FA alpha does not involve time derivative. That is a direct case. And we can say that this also applies to internal symmetries. Okay, internal symmetry means the transformations that does not involve the space-time coordinates. So they are known as internal symmetries. Okay, example for internal symmetry is the phase rotation of a complex scalar field. Okay, so for such symmetries, the transformation will not contain time derivative. So if you take the current J alpha, then I can write it in terms of the Lagrangian density. Okay, so here it is 0, which means the time component. So here I have to write del 0 phi a, then f a alpha minus k 0 alpha. Okay, so derivative of the Lagrangian with respect to time derivative of the field will give the canonical conjugate momentum density, right? So this will be pi a, because the derivative of the Lagrangian density with respect to the time derivative of the field will give canonical conjugate momentum density. And here we have taken the condition that this FA does not contain the time derivative of phi a, and also FA alpha does not contain this term K0. Okay, so K0 must be 0. So if I apply K0 is equal to 0, then I'll get J alpha 0 is equal to pi a FA alpha. So here the term FA alpha does not contain any term with derivative of the field. Okay, and also I have taken K0 alpha equal to 0, which means my current density is now pi a FA alpha. In classical mechanics, you can write this expression in any order, but quantum mechanically, here FA alpha involves the field phi, okay, and the momentum does not necessarily commute with phi. So FA can be a function of phi, right? And if I write it, I cannot write J alpha 0 in any order. I cannot write FA alpha of phi first and then pi a next, because they necessarily do not commute. Okay, so that is also there. So you have to be very careful, because in classical mechanics you can write this expression in any order, but in quantum mechanics you cannot write. So here you have a potential operator ordering ambiguity. Now let's take the commutator epsilon alpha q alpha with respect to phi a of x. Okay, so I want to find this commutator. Okay, I have to find this commutator. So this will be equal to integral. So I'll substitute 1 by 1 d cube x prime epsilon alpha as it is, and q alpha will be pi a of x prime, right, f. So I am not writing the same a, I can write fb. Okay, b here, a and b labels the different fields. Alpha x prime comma, now this will be commutating with the field phi a. So phi a of x. So this is equal to integral of d cube x prime epsilon alpha. Now here we have already taken the condition. Now we are seeing the case for which fb alpha of x prime, okay, does not contain any term with the time derivative of the field, which means that there is no momentum inside the fb. Therefore it commutes with phi a and I can take it outside. And phi a of x prime comma phi a x. Okay, so here I will get this is equal to, right, so I can take out epsilon alpha and fb alpha of x prime. Okay, then I can integrate pi a and phi a. So the integral of the commutator pi a phi a will be I del cube, minus will come because phi comma pi will be I del cube x minus x prime, right? But here I have pi a comma phi a, which means there will be a negative sign also. Okay, and this will survive only if x is equal to x prime. Then I can substitute this is equal to minus I epsilon alpha fb alpha. So x or x prime, I can write anything, right? Even if it is x or x prime doesn't matter because x is equal to x prime, right? So I have proved that the commutator of the charge and the field will give rise to an infinitesimal transformation, right? Now I will see the case 2. Okay, I will call the case 2 as time translation. And the best example for time translation is the Hamiltonian density itself. So I can write the Hamiltonian density is equal to pi a, right, and then the time derivative of the field minus Lagrangian density. So if you carefully look at this expression, this is the current density and this will be the transformation, and the Lagrangian density will act as the k mu alpha. Okay, so the first case was a limited case, but here second case it's not a limitation, it's a complicated, much more complicated, because here you have a non-zero k, right, and a transformation which involves the time derivative of the field. So this is more complicated. And the conserved charge here will be the Hamiltonian h, because that is the integral of the Hamiltonian density. So by definition, Hamiltonian acting on any field, okay, the commutator will be minus I phi a. Okay, this is the time transformation of fields. Therefore Hamiltonian can now be considered as a symmetry generator for time translation. So when it acts on the field phi a, it generates the time translation, okay, which is infinitesimal time derivative of phi. Therefore Hamiltonian can now be considered as a symmetry generator for time translation. Okay, so what we have seen till now are the infinitesimal transformation. We can also obtain finite transformations from the charge q. So let's see the finite transformations. Okay, so let consider u of lambda alpha is equal to e raised to I lambda alpha q alpha. Okay, so let this be an operator. Here lambda alpha is a collection of finite transformational parameters. Okay, and these parameters are used to generate finite transformations. So lambda alpha is a collection of such finite transformational parameters. And a finite symmetry transformation of the field phi a can be represented using this operator as u of lambda alpha acting on the field phi a, you will get phi a prime. Okay, so this is a finite symmetry transformation. So this is not infinitesimal, this is finite symmetry transformation. So if you put lambda alpha is equal to epsilon alpha in such a way that epsilon alpha tending to 0, then this equation will reduce to the non-trivial order, right? So when you expand u of lambda alpha is equal to e raised to I lambda alpha q alpha. Okay, this is an exponential term, so you can always have a series expansion. Okay, when you expand and then with alpha as infinitesimal, then the leading order term will become minus I epsilon alpha fa alpha. So we can imagine this u of lambda by finite number of infinitesimal transformation, and building them up we can generate the finite transformation, right? So in this limit you will get infinitesimal transformation, and the actual finite transformation is actually built by generating many infinite number of infinitesimal transformation and then building them up. So one example, if you see, then you e raised to I ht minus I pi xi acting on phi 0 0. Okay, so this is one example for the symmetry transformation, finite symmetry transformation. So this will be equal to phi of t comma x. Okay, here this ht minus pi xi is equal to lambda alpha q alpha. Okay, so alpha can take 0 and I. Lambda alpha here is t from here and the xi from here, so t comma xi, and q alpha here will be the Hamiltonian and minus pi from here. Okay, then another example is the Lorentz transformation. So next example will be Lorentz transformation. So in Lorentz transformation, the conserved charges m mu nu, okay, with mu comma nu runs from 0 to 3. Okay, so then it will have 3 rotations and 3 boost. So this will have 3 rotations and 3 boost, and this will correspond to 6 conserved charges. 6 conserved charges. So when you write the finite transformation, then you will have 6 parameters. So u lambda will be e raised to I omega mu nu and m mu nu. Okay. So here we already know that the Lorentz matrix is antisymmetric. Therefore, omega mu nu must be equal to minus omega nu mu. So this must also be antisymmetric because there are finite angles of rotation. So these are all finite angles of rotation. So if m mu nu, the Lorentz matrix is antisymmetric, then this should also be antisymmetric. So u lambda will act on phi, right? And you will get phi prime of x. So this phi prime of x is nothing but phi of lambda acting on x. So here lambda inverse x is the Lorentz transformation of x mu. Okay, is the Lorentz transformation of x mu. Good. Now another example for finite transformation is the phase rotation for a complex scalar field. So we can show that there is a Noether charge corresponding to the phase rotation and there is a Noether current corresponding to the phase rotation of a field. Okay, so that will be a symmetry and this generate a charge Q. For example, okay, so I'll write the phase rotation and we will see this in detail in the next section, that we will very soon go to the next section. Okay, the complex scalar field. So here e raised to I alpha q, here q is the charge, when it acts on phi of x, then I get e raised to I alpha phi of x. So we see that it generates a phase rotation in phi. So with this we are concluding the discussions of the real scalar field and let's move on to the complex scalar field. So we'll see this in more detail in the upcoming session. So the next topic will be complex scalar field and antiparticle. If the field phi is a complex scalar, then phi star will be its complex conjugate, right? So till now we have seen phi as a real scalar field. Now phi is a complex scalar field, which means if phi is a complex scalar field, then phi star will be its complex conjugate. Therefore the Lagrangian density will become minus del mu phi star minus m square phi star phi. Okay, so now phi is a complex number, means phi will be of the form a plus ib. So we can decompose the field phi into 2 parts, right? And each part will have a real number a and b. Okay, we can decompose phi into 2 parts, the real and the imaginary part, and if you plug them into this Lagrangian, then you will get 2 copies of the equation for the free scalar field, because here a and b are 2 real numbers, and if you again plug it back to the Lagrangian, you will get 2 copies of the equation for a free scalar field. So one is the real scalar field for the real part, another one will be the free scalar field for the imaginary part. Then what is new in this form? If you are getting the same form of equation, then what is new in this form? The advantage is that we can incorporate a new concept when you write the complex form of the Lagrangian. Rather than writing it as a two separate identical scalar field theory, you can represent it in this form, so that the advantage is that there is a new concept that is arising. Okay, so if you do the transformation e raised to I alpha phi, we can immediately see that the phase symmetry is manifested. Okay, so this corresponds to a rotation between the real and the imaginary part. Okay, the rotation between the real and imaginary part is represented by this phase rotation symmetry. Now, the canonical conjugate momentum density in this case will be, and the canonical momentum corresponding to phi star will be del naught phi. So we can treat phi and phi star as two independent fields. Okay, so phi and phi star are two independent fields. So the equation of motion also will have the same form. Okay, so del square phi minus m square phi is equal to 0. Okay, so this will be the equation of motion. It will also have the same form, and therefore the basis of the general solution will also remain the same. Okay, the basis will also remain the same, e raised to minus I omega t plus I k dot x, and you have uk star e raised to I omega t minus ikx. Okay, so first I will write the general solution in the classical form. So that will be phi of x will be integral d cube k by 2 pi cube 1 by root of 2 omega k ak uk. Okay, and in the previous classes I used to write a star uk star in the next term, right? But now onwards I'll write bk star uk star. So there is a small difference from what I have done in the real scalar field theory. When you come to complex scalar field theory, here phi is not real. Here phi is complex number. Okay, so earlier in the real scalar field theory we used to write a star, but here I have replaced it with b star. Since the classical field is not real, when you convert it into quantum, the quantum field will not be a Hermitian operator, right? So if I promote it to an operator, since it is not real, since the field is not real, when you convert it into, or when you promote it into the operator form, the operator, field operator, will not be Hermitian, and therefore I have to introduce here a and b both. So this will be equal to integral d cube k by 2 pi cube 1 by root of 2 omega k operator ak with the basis uk plus bk dagger uk star. Okay, so by taking the complex conjugate of phi, I will get phi dagger of x. So here phi is not Hermitian, therefore phi is not equal to phi dagger. So what is phi dagger? Phi dagger is equal to integral d cube k by 2 pi cube 1 by root of 2 omega k ak dagger uk star plus bk uk. This is the phi dagger. Now we have two sets of creation and annihilation operator. One is ak dagger and bk BK dagger. So it makes sense because when you have a complex variable, you double the degrees of freedom and your integration constant will also get doubled. Okay, so that's very important. And here one more thing is that BK is independent of AK. BK is independent of AK. Similarly, phi dagger is independent of phi. There is no connection between them. Okay, therefore I can write the equal time commutation relation. Phi dagger is equal to phi which is equal to phi dagger is equal to pi phi. So these are all independent is equal to 0. So they are considered as independent operators so that they should commute with each other. So they are all field variables. And as usual, we have phi of t comma x prime of t comma x is equal to I del cube x minus x prime, right? And similarly for phi dagger of t comma x prime, phi dagger t comma x prime, x is equal to I del cube x minus x prime. To save the time, I am not writing the expression, but all of this must be evaluated at the same time but at different spatial locations. So I am writing AK dagger, prime dagger is equal to 2 pi cube del cube of k minus k prime. Similarly, BK prime dagger is also equal to 2 pi cube del cube of k minus k prime, and all the other commutators vanish. So you can almost guess everything without doing any calculation. Okay, so now we'll move on to the real difference. What is there in this complex, right? So we'll move on to that. What is the conserved charge here? The conserved charge in the case of a complex scalar field, Q is equal to integral J0 d cube x. So we know this. And what is J0 for a complex scalar field? For a complex scalar field, J0 will be I cap phi dagger dou phi by dou t minus phi dou phi dagger by dou t. Right? This we have already seen. So this will be equal to, so when I substitute phi dagger and the time derivative of phi, okay, then I integrate with respect to the space, then the remaining thing will be integral d cube k by 2 pi cube 1 by 2 omega k, then AK dagger AK minus BK dagger BK. This will be the conserved charge, and the Hamiltonian will be integral d cube k. In a similar way, I can also find the Hamiltonian. I am just writing the final answer. It will be AK dagger AK plus BK dagger BK. So the sum of the harmonic oscillator corresponding to AK and BK will give you the total Hamiltonian. Okay. So what will be the ground state here? So the lowest energy state or the ground state will be the state that is annihilated by both of the operator. That is the annihilation operator. Okay, when it acts on the lowest state, you should get 0. So the state that gets annihilated by both the annihilation operators are known as the ground state. Similarly, I can have AK dagger acting on 0 and BK dagger acting on the ground state. So we can have, so what do you mean by AK dagger acting on the lowest state and BK dagger acting on the lowest state? So in the last class, the last lecture, we have seen that these are nothing but excitation of the particles. So we can have two type of particles here corresponding to AK dagger and BK dagger, because there are two type of excitation that is happening here. Okay, so we can have two type of particle generated by AK dagger and BK dagger respectively, and both particles will have the same mass, okay, as all of them come from the same equation. What is the equation? D square phi minus m square phi is equal to 0. So this, both these come from the same equation, therefore they will have the same mass. If the two particles have the same mass, and by definition we know they are all spin zero scalar particles, because I have not considered spin yet, then how do you differentiate between these two particles? Okay, so how do you tell them apart? That is a question. Then you have to use an internal symmetry to find it out. So here we use the phase rotation that we have discussed. So we have discussed this phase rotation e raised to I alpha phi. So this is a symmetry. Mathematically, this is called the U1 transformation. So no need to worry by hearing such a name. So U1 is just a mathematical term for phase rotation. Okay, so mathematical name for phase rotation. So this way to distinguish two particles is to look at their quantum number. So we get one more conserved quantity corresponding to the U1 symmetry. So by definition, when you are at the lowest energy, there is nothing there, right? It is a vacuum. Therefore, by requiring the lowest energy state to have a charge 0, right? So how do you say that the lowest energy state has no particles and therefore it should have a charge 0? Then I have to operate the charge Q onto the lowest state and I should get 0, right? So what is Q? I have already obtained Q. Q is integral d cube k by 2 pi cube AK dagger AK minus BK dagger BK. Right? This I have already obtained here. AK dagger AK minus BK dagger BK. So when you write in this form, what happens? This AK dagger AK. So when Q acting on 0 means here the AK will first act on 0, right? We have written this in such a way. Okay, it's called normal ordering. Normal ordering means the annihilation operator always come to the right side of the creation operator. So we write it in such a way that it first acts on the lowest state. Okay, so when you write it in this form, AK dagger AK will act on the lowest state and AK will annihilate the vacuum. Okay, so I can write it in terms of number operator as well. AK dagger AK is the occupation number for AK. So I'll write it as N AK minus N BK. So here the minus sign is the key. So when you operate the commutator, okay, this minus sign is the key, because when you operate Q comma AK dagger commutator, you will get AK dagger. But when you do the commutator of Q and BK dagger, you will get minus BK dagger because of the minus sign that is sitting here. So that means if you look at the state corresponding to AK and BK, so these are just the commutators. Now if I see the state K is generated by, in the previous class we have seen this is a normalization constant. The state K is generated by AK dagger acting on 0. Similarly, if BK dagger acts on 0 with the normalization, then I will get K bar. Okay, I represent this by K bar. So that means if you look at the state corresponding to AK and BK, when Q acts on K, you will get K, and when Q acts on K bar, you will get minus K bar. So K and K bar have same mass and spin 0 but opposite charge. They have opposite charge. In that case, okay, when you have two particles with all the quantum numbers are the same except that they have opposite charge, we call them particle and antiparticle. Okay, so Q acting on K equal to K is particle. Then I can call Q acting on K bar equal to minus K bar as antiparticle. Therefore, we can show that in any relativistic quantum field theory, each particle has an antiparticle. And in the case of a real scalar field, you have only one type of particle. In that case, the antiparticle will be itself, right? So this means that the property of particles and antiparticles are almost the same, except that they have opposite charge. So just like the real world, we have matter and antimatter. They have essentially identical properties. And if the world is made of antimatter, everything will still behave the same. Okay, except that the charge difference will be there. Otherwise, all are the same. You cannot differentiate between a particle and an antiparticle, right? Therefore, I can write in any relativistic quantum field theory, each particle has an antiparticle. So that's how the concept of particle and antiparticle can be explained in quantum field theory. Okay, so for today we stop here.